Hello everyone, this is Mr. Appel, and today we're going to do a little review and talk a little bit about word problems, modeling situations, modeling real-world situations or quasi-real-world situations, and using algebra and other things that we know to help solve them. So just a quick overview of a sort of general strategy guide. Obviously read the problem carefully, that's important, and we're generally going to let X represent your unknown, the main unknown in the problem. Now there may be more than one unknown, so if there's more than one unknown, you want to try to write them all in terms of X, and I'll try to show what that means in the next couple of examples. Then we're going to write an equation that models the conditions of the problem, that fits the situation that you are given. And that's going to be, you write the equation, then once you've done that, you solve the equation to try to answer the question. And again, it's important that you answer the question. Finding X isn't always answering the question, so you need to go back and answer it. And then, of course, checking that your answer actually makes sense. What you're going to see coming up are sometimes situations are linear, sometimes they're quadratic, and sometimes they're rational. And those are the type that we're going to focus on here in this little mini unit. So let's look at an example. There are multiple different ways to sort of represent a situation. So I want to show you a numerical way to represent this situation here. So this company finds that producing an engine, it costs $5,000 in fixed costs plus $2,500 per ton produced. So a numerical way to represent that, notice it's increasing per ton. So maybe I look at the number of tons versus cost and I actually list them. So for 1 ton, the cost would be the 5,000 plus 1 ton, so that'd be 7,500. If I added another ton, it's still the 5,000 in fixed cost, but now it's 2,500 per ton, so that's 2 2,500s, so that's 5,000 plus the 5,000 is 10,000. And if I add another ton, I'm adding another 2,500, so that's 12,500. And so on. And sometimes writing this out like this can show you what's happening. It's easy to see that this is linear, it's increasing at a steady rate. Another way to explore this kind of situation is graphically. So I'm looking at tons, what's changing are tons and what that's impacting. So this is the independent variable is the tons, and the cost depends on the ton. So this would be your cost. And so maybe for 1 ton would be here at 7,500, and at 2 tons would be up here, and you'd have to put a scale. But the idea is you'd be able to see from that it's increasing at a linear rate. So that's another way of representing or modeling a situation. And then algebraically. So if we let X equal the number of tons produced, then we'd have $5,000 plus 2,500 times the number of tons. And maybe Y is our output, it's our total cost. So that's an algebraic representation. Okay. Let's look at an example. So we have a computer store having a sale on cameras. After 40% price reduction, the cost that you purchase it for $276. So that's after the price reduction. What was the camera's price before the reduction? So I'm going to let X be the price before the reduction. So if I take X and I reduce that price by 40%, I have to think about how would I do that if I knew what the number was, if I knew what X was. Well, there's more than one way to do that, but one way to do it might be to say, all right, let me take that price, and then I would figure out what 40% of that price is and subtract it. Well, how do I find 40% of the price? I do 0.4 times that price. So if I take the original price and I subtract 40% of that, that should give me the purchase price, the new price, which in this case is $276. So that's kind of how you reason through this problem. And if we simplify over here, we'd get 0.6x equals 276, and then we could divide by 0.6, and I guess I should do that. 276, sorry, you can't see that on your screen. 276 divided by, where's my divided by? There it is, divided by 0.6, and I get $460. $460. I'm then going to answer the question, so the price before reduction in this case was actually X, but it's $460. And I'm thinking, does that make sense? Well, if my original price was $460 and it was reduced by 40%, that's a little more than half. Well, half of $460 would be $230. $276 is a little more than that, so that does seem pretty reasonable. That seems right to me. Another way to do percent reduction is, instead of to say reducing by 40%, think about how much of it is being kept. So if you have something that costs X dollars, if you take away 40% of the price, you're going to be left with 60% of the price, because of course the whole price is 100%. So you could just say 60% of the price should be $276, which is of course what you have right here. Two different ways of thinking about it. Either way is okay. Okay, let's look at another example. The length of an American football field is 200 feet more than the width. So let's let X equal the width of the field. And now I want to express the length in terms of the width. This I mentioned at the beginning. I want to express it in terms of the width. I don't want to introduce another variable here. There are times when we'll use a second variable, but I want to avoid it. So if X is the width, the length is 200 feet more than that. Okay, so X plus 200 would be the length. Okay, and that way I'm using X to represent both. And now I can think about perimeter. Well, perimeter is just twice the length. Well, I can't write. Twice the length plus twice the width. So that's twice X plus twice X plus 200. So twice the length plus twice the width should equal 1,040. And there's my equation. And now we can solve that algebraically. So that ends up being 4x plus 400 equals 1,040. Subtract the 400, which is 640. So x equals 432, 16. I mean, sorry, 160. So x equals 160. Great, I'm done. No, I'm not. That's not what the question said. The question didn't ask me what x equals. It asked me what are the dimensions of the football field. So if the width, x is the width, then the width is 160 feet. And the length is 200 feet more than the width, so the length is 160 plus 200, which is 360 feet. Okay. And just checking to make sure that that makes sense, if the length is 360 and the width is 160, the length plus the width, 160 plus 360 is 520, but then the other length plus width would be the other 520, and it does in fact give us a perimeter of 1,040. So this is the answer to my question. That's all for now. Now those led to pretty simple equations. You can imagine they're going to get more sophisticated. They're going to lead to quadratics, they're going to lead to rationals, but we'll do more of that practice together in class. Take care, bye-bye.